So continuing with this list of matrix terminology, we say that a matrix is upper triangular if all the entries below the diagonal are 0. So upper triangular means that whenever I is greater than j, it has to be the case, or it follows that the ijth entry is equal to 0. So for instance, this is true if we take something like 1, 3, 0, negative 1. So this is a 2 by 2 upper triangular, and B, so we take B to be something like this. So wow, that came out a little crooked there. There we go. That's slightly better. Okay, so the idea should be that just anything below the diagonal should be all 0. So in some books they'll write this as 1, 4, 1, 0, 2, 3 with just a big 0 right here like that. Usually I will write it like this with just a big blank spot, and if there's a big blank spot there, then you know that all the other entries are equal to 0. So notice, by the way, that there's a 0 on the diagonal right here. That's fine. That's completely legitimate. It's not that the zeros have to be below the diagonal. It's that anything below the diagonal has to be a 0. Okay. So, and then we similarly say lower triangular. So this is j bigger than I implies aij is equal to 0 if all the entries above the diagonal are 0. So for instance, if we take A transpose and we rewrite the rows as columns, then we'll have 1, 3, 0, minus 1. And so that will be lower triangular. And B transpose will be, let's see, so 1, 4, 1, 0, 0, 2, and what was the last one? 0, 0, 3. There we go. And so again, now we're just looking to make sure that everything above the diagonal is 0. And then it's possible to have it be the case that a matrix is both upper and lower triangular, and then it's called diagonal. And so an example of a diagonal matrix, so maybe something like this. And so again, by those blanks being left there, you should assume that anything in here is a 0, and similarly down here. We also say that a matrix is symmetric if it's equal to its own transpose. So in other words, if A is equal, or if A transpose is equal to A again. So an example of a symmetric matrix might be something like this one, or for a 3 by 3 example, say 3, 0, minus 1, so we need to have a 0 and a minus 1 to match those ones. And then say 4, and if this is a 5, then this better be a 5, and this is maybe a minus 2. There we go. So the way that I drew that in there, you can see that in order for a matrix to be symmetric, it needs to be the case that aij is equal to aji, so that it looks like it's reflected along the diagonal. Wow, that totally made a mess of it. Let me get rid of that. Reflected along the diagonal like this. So in other words, these two entries need to be the same, and these two entries need to be the same, and these two entries need to be the same. So it looks like it got flipped across the diagonal. So then we say that a matrix is skew symmetric if A transpose is equal to minus A. And so minus A means that I take the negative of each entry. So this means that Aij should be equal to minus Aji. Okay, so for an example of a symmetric 2 by 2, let's see. We could make, well, what should we have for the first entry here? So now this is going to be the same as the corresponding entry of the transpose, right? The 1, 1 entry of A will be the 1, 1 entry of the transpose. But the rule is that the 1, 1 entry should be equal to the negative 1, 1 entry. The only number which is its own negative is 0. So this has to be a 0. And same for the one down here. And then if I put, say, a 3 here, then this would have to be a minus 3 down here. So let's see. So I'll do a 3 by 3 example. And again, I know that it's going to have to be 0 everywhere down the diagonal. If this is 1, this is going to be minus 1. If this is 3, this is going to be minus 3. And if this is 4, then this is going to be minus 4. So there's a 3 by 3 skew symmetric matrix. And the last idea we have is that of a matrix function. So a matrix whose entries are functions of a single variable is called a matrix function. And so you've seen examples of this, for instance, in your calculus courses. So suppose we have cosine t, sine t as the entries of a 2 by 2 matrix. Then you know this is a curve. This is a standard parameterization of the unit circle. Right? So this is going to be going, whoops, hey, hold still. Counterclockwise, starting from here. And this is a function. It takes a single variable t right here. So t maybe lives in some interval, maybe like this. And it maps those points into the plane. So over here's a copy of R2, the plane. And C is a function or a mapping that takes the single variable t and plants it into the plane according to some rule like this. You've also seen this when you did parameterizations of a line, for instance. So if L of t is 3t minus 1, 4, and 1 plus 2t, then this is some line in R3. So if we've got some three-dimensional space like this, okay, then this line is going to be some, who knows what. Let me see. Well, I guess I can tell you that the second coordinate is always 4. So it's going to be passing through this point, and I don't know what it looks like. I'm just going to draw some random line. There we go. So there's this line.